by month. The checked off ones are the ones that we've already done, and the PowerPoints are available at the Google Share folder, which Hillary put on the advertising pages. For July, the theme is supposed to be physical and mental health. Well, you know, there are many different ways of thinking about this. Of course, the sun and having sunlight is important to our circadian rhythm and basically our general state of being happy.
Hey, Ro, couple quick things. One, Sandy said that they didn't want the scaffolding to get wet.
I'm sorry?
Well, I figure maybe tomorrow morning we could.
Yeah, thank you. So anyway, you know, mental health and the sun seem to go together, especially if you have seasonal affective disorders or things that require lots of sunlight to keep your circadian rhythm going. But what I thought would be interesting to do is to look at some other issues. Let's see. NASA tends to partition its research, at least in retrospect, into answers to three sort of large questions. In heliophysics, those big questions are what causes the sun to vary? How do the Earth and the heliosphere respond to the sun's variations? And what are the impacts on humanity? These big questions form the basis for what we call the framework for heliophysics education. And for those of you that are educators, this is a fairly granular way of looking at these three big questions at the level of the national science standards. And here what we've done is to create three subsidiary questions that link directly to the national science standards so that the correspondence is easier for teachers to see between the three big questions that NASA works with and ones that are more bite-sized and chewable in the classroom. This presentation is going to be about standard 2.3 in this list. The sun is the primary source of light in the solar system. Well, you know, the particular take that I have on this is that I'm going to talk about sunlight and ultimately the origin of sunlight, since that's what the heliophysics aspect is. Heliophysics does not include the study of human psychology or biophysics. So I have to retranslate the monthly themes into things that sound like they're related to heliophysics. And that's actually kind of a fun challenge. Each month I've been challenged, you know, to do this. Especially a couple of months ago, we had the theme of fashion. And so I talked about the nature of color and filters, which are important to fashion, at least as I'm told. So anyway, physical and mental health. Okay, one thing that we use to gauge at least our physical health is the number of steps that we take every day. And there's this sort of magic urban legend number of 10,000, but it turns out 10,000 steps is not really connected with anything in terms of physical health. It just happens to be a number whose word in Japanese matched another word in Japanese used as part of an advertising slogan. So it doesn't really have any physiological import, but however, you know, generally it's better for us to take more steps during the day and keep active than taking fewer. And we can figure out, you know, roughly how long it takes for us to take those many steps and how much of your day, you know, needs to be occupied by some form of movement. Anyway, so what we could do, let's see. Well, okay. As sort of a beginner's math,
I'm just trying to be quiet in case
approach to this, what we could do is, you know, if you average 5,000 steps a day, and each one of these steps takes about 1 second, how much time do you spend every day walking, or at least counting up your steps? And that is a pretty straightforward thing to do. You basically take the number of steps each day, multiplied by, say, 1 second per step. I sort of measured this myself for me, and that's a kind of a comfortable gait, you know, that I can maintain. So that works out to be about 5,000 seconds a day, and there are 3,600 seconds in an hour. So you get about 1 hour and 23 minutes worth of walking to get to the 5,000 steps. So anyway, if you want to see where you lie on this particular scale, get yourself one of these free apps and power it up and, let it keep track of how many steps you're taking each day. I personally think that, taking between, 1 to 3,000 steps a day, is probably a very good goal. It's not very intrusive, and you can do it walking around your kitchen, washing dishes, going up and down the stairs to the laundry, any number of things. And it all adds up in the course of a day without you even knowing that you're actually doing this. Okay, let's take another step here. If each step takes about a second, and each one of these steps is about 7/10 of a meter long, how long would it take you to walk to the sun? Okay, now we're getting into deep heliophysics because I've just mentioned the word sun. Okay, so I know I'm on the right track with this particular problem. Distance to the sun is 150 million kilometers. And here's a pretty picture of the sun at sunset. So anyway, it's pretty straightforward. One step is 7/10 of a meter. 1 kilometer is 1,000 meters. 150 million kilometers times 1,000 meters in 1 kilometer. You basically get about 150 billion steps or so. And one step is going to take a second. So 150 billion of these babies takes about 4,800 years. So anyway, it's quite a commitment, if you feel like doing this. But you'll probably poop out even before you get to the edge of the Earth's atmosphere. So not to worry. Now we come to an interesting problem, and this is sort of at an intermediate level. Starting from the center of the sun, how long does it take a photon of light to get out from the center of the sun, reach the surface, and then 8.5 minutes later wind up on your doorstep? That is something that is a more complicated thing to calculate because these photons, they act like balls in one of these pachinko games or on a billiard table. They get bounced around quite a bit. They collide with atoms and get absorbed and re-emitted in different directions. And so you can see that the more tightly packed the atoms are, the more of these steps the photon is likely to take. And the less dense the sun is in its outer regions, the farther it can travel in one step. So it's kind of a complicated problem because the step size is continuously changing from the center of the sun to the edge because the density of the sun changes over this scale. What we could do is sort of approximate this. Well, first of all, let's take a look at this problem. It's called the random walk problem. If you draw a two-dimensional grid and you mark it off in cells that are one step in size, each one of those cells represents one step. What you do for random walk is you use a coin and you flip it 2 times. The first time you flip it, that'll tell you whether you're going to go along the x-axis direction or along the y-axis direction. The second coin that you toss will tell you if you're going to take a step up or a step down or a step left or a step right. So basically this process is one that you can simulate yourself. If you have a lot of free time and start out at the origin and see how far you get after a few hundred of these steps. Each one of these patterns that you see here is going to be absolutely unique because when you flip a coin 200 times, there are a lot of possibilities for variation between one path and another. But the interesting thing is that you can use ChatGPT as a simulator as well, and this gets you into some interesting stuff. If you put in the query, in 2D, perform a random walk simulation and calculate the distance traveled after 16 steps if each step is 1 unit in length. I asked ChatGPT to do it for 5,000 steps because I was sort of impatient. And so on the right-hand side, you see what the ChatGPT response was. It told me what it was doing. Each one of these stages in the calculation was exactly as it should be. And so the bottom line was after 5,000 steps, it got 65 units away from the origin. That's how far it traveled. You could do this over and over again. Create a model in which the distance traveled is given by the formula distance equals the step size times the square root of the number of steps. And so you see in this table, we've got column 1 is the number of steps. Column 3 is our square root of n model. And then we had ChatGPT do the calculation as it did before, and it came up with the numbers in the middle column. What you see is that our model, which follows the square root of n relationship, is actually pretty accurate. And in fact, if you carry this out even further on the next slide, you can actually plot what ChatGPT provided, which is the black dots, and what the actual thing is, which is the yellow dots, and you draw a line, which is the red. And that line, if you smooth it out, is basically the square root of n as the distance traveled. So on this plot, if you go 6,000 steps that are 1 unit in length, if you follow the vertical line up to the red line, it requires about 75. You will get about 75 units away from the origin, taking that many steps. And it increases fairly slowly with the increasing number of steps. It's a very sluggish process. We can actually sort of plot this for a large number, and we can ask the question, if you take roughly a 2-foot step, how many steps will it take you to travel 1 mile from where you started? Well, we can simplify this problem because, let's change it to 1 kilometer instead of 1 mile. That way we can work in the metric system, which is the one I'd prefer to work in. So yeah, this is a typo on my part. And if we follow that using the square root of n, to go 1 kilometer away, that's d is 1 kilometer, taking steps that are 0.7 meters in length, then you basically work backwards and solve for what the value of n is, following the steps in the first column there. And you get about 2 million steps that you have to take in order to get 1 kilometer away from where you started. And if you take 1 second per step, it's going to take you about 23 days. So if you start out at your local 7-Eleven and you take a random walk home, you can be prepared for it taking a very long time to get home. So I would not recommend that.
Gabriel had a question about that formula.
Yep.
More detail about how you derived the formula?
That's basically a fit after the fact to the data. So I kind of cheated. But what you could do is you could go back, you could put this data into an Excel spreadsheet and then try different values for a polynomial, and you'll find out that a quadratic fit to these data is the best fit. It's not linear. You can look at this and you can see that it's not going to be linear. So the next complicated is a quadratic, which is a power of x to the second, and that fits the data pretty nicely. So that's kind of what you do. Anyway, what you can see in this plot on the right, you can see what happens when you essentially compare one random walk against another random walk and against a square root of n model, which is shown in green. And you find the square root of n model works really very nicely, at least over this particular range of steps. What we're going to do, though, is we're going to say, okay, suppose this random walk law, the distance is the step size times the square root of the number of steps. Suppose that can be applied to the sun and the way light escapes from the center of the sun. Now, the problem is that the density at the center of the sun is almost the density of lead. And by the time you get out to the upper atmosphere, which is what we see from Earth, you're down at something that's almost like a very good vacuum. So the density range is enormous between the center of the sun and its surface, which means that as you go towards the surface, the atoms are being more and more spread out. The distances between them get longer and longer, which means that the photons travel farther before they get scattered into some other direction by colliding with an atom. An awful lot of these collisions and short distances happen towards the core, but by the time you get out towards the upper atmosphere, the convection, the photosphere, those regions, all of a sudden you're talking very long distances that you can almost measure with a ruler. We're going to use this approximation that in the core of the sun out to about 140,000 kilometers, that's sort of that white area in the figure there. Let's assume the step size is about 1/10 of a millimeter. And then going from the edge of the core out to the surface, it's about an average of 3 millimeters. We'll just start with that and see what we wind up with. The way to properly do this is to use an actual mathematical model, excuse me, of the interior of the sun. And that model is based on fairly tight physical relationships between atoms, the properties of the atoms as they scatter light, and the density and temperature of the sun at each location. But we're not going to use that kind of a rigorous model. But it actually turns out that this approximate model that I have here works almost as well if you just want a ballpark number. So we're going to start with that. The first region is the core. Step size is 1/10 of a millimeter. And so we work out how many steps you have to take at 1/10 of a millimeter to travel 140,000 kilometers. And we've seen a problem like that before at the intermediate level, where we calculated the number of steps to go 1 kilometer if your step is 7/10 of a meter. So it's the same problem, just applied to a different context. It turns out when you solve for n, you get about 2 times 10 to the 24, which is 2 trillion steps. Now, light travels at the speed of light, not surprising. So basically, you multiply this 0.1 millimeters divided by the speed of light to get essentially how long it takes per step for light to travel 1/10 of a millimeter. And then you multiply that by 2 by 10 to the 24 steps. And so you wind up with the number of about 21,000 years. So very crudely, it takes about 20,000 years for light to get from the center of the core out to the edge of the core. And then we have the second zone, which is physically different than the core. It's at a lower temperature, and it's at a significantly lower density on average. In this case, the radius of the sun is 690,000 kilometers, and this zone is subtracting the radius of the core, which is 140,000 kilometers. This second zone is about 550,000 kilometers thick. Okay, so now the question is, with a step size of 3 millimeters, how long does it take the photon to travel 550,000 kilometers? So it's an analogous problem to the first one. In this case, it only takes you about 3 by 10 to the 22 steps because you're able to travel farther on each step than you were in the previous situation. And so now when you multiply by or divide by the speed, by the speed of light and do that particular calculation, you travel about 1 by 10 to the minus 11 seconds per step. And so over 3 by 10 to the 4 by 10 to the 22 steps, it takes you about 11,000 years. So if we add up both of these numbers, we get something that's like 32,000 years, give or take, to travel from the core out to the edge of the sun. There are various ways of doing this particular calculation. It's a popular one, and it all depends sensitively on the step size that you use. The worst thing you can do is to calculate the average density of the sun. From that, calculate the average distance between particles, and you get something like a centimeter. That gives you the worst answer. Other answers, if you use something that's primarily the density of the core of the sun as the average, then you'll get a time scale that's in close to 100,000 to 1,000,000 years. So breaking the sun down into these two zones that have different densities for good physical reasons is sort of the best compromise. And it's the one that's based on the most knowledge that we have. Again, it turns out that if you do this calculation using the actual change in density within the sun and follow that carefully, you get numbers that are anywhere between 30 to 60,000 years for the average time it takes light to get out from the center of the sun. So we're in the right ballpark, and it just goes to show you how you can use something like the random walk problem, to get you some information about a physical system like the interior of the sun, which is something that you normally can't, sort of talk about in any other way. Well, that's about it for the random walk problem. Next time, August, the theme is back to school, and I thought it would be fun to look at the life cycles of stars and their remnants. So we're going to talk a little bit about white dwarfs, neutron stars, and black holes. I know we ended kind of early, and so that allows us a lot of time for questions and answers, because I thought that would be a kind of a fun thing to do this time. Of course, for the next talk in August, I'm sure there are going to be a lot of questions about black holes. So that'll be a lot of fun too. Anyway, so random walk problems. If you have any questions about them, let me know. And I guess I'm going to stop sharing at this point.
And I put in the chat the YouTube recording, which I'll post later and today or early tomorrow. And then the slide decks, I put in the link for that. So if you want to go through it again.
Right.
Gabriel had a question about, well, why don't you say, Gabriel, and just unmute yourself. You'd like to go through the first set of computations?
Right. I just like to see you walk through your steps with the first problem again. I didn't fully understand.
Oh, okay. Well, let me go and reshare. Share.
Hope it isn't too much trouble.
There we go. All right, first problem. That was what? This one?
Oh, no, I mean the first of the advanced problems.
Oh, first of the advanced problems. Beginning, intermediate, and advanced. Okay.
Is that it, Gabriel?
Yes.
Okay.
All right. That's the setup, and this is the first. This is the actual computation. I really do hope I got the powers of 10 right. Anyway, yeah. What was the question?
Could you run through that first computation that you did again? I was having difficulty following your algebra.
Right. Well, it's related to this one here, where we started with each step was 7/10 of a meter, because that's a normal human step. And the question was, how many steps does it take to go 1 kilometer? And we're using this distance equals step size times the square root of n as our law that relates these two things, the step size and the distance. And then we basically, what we do is it's 1 kilometer. So we're taking 1 kilometer, dividing it by 0.7, and that's equal to the square root of n. And that happens in like the line 3, where we have n equals 1,000, which is 1 kilometer is 1,000 meters, divided by 0.7 meters. And then to get rid of the square root of n, we square both sides. So we wind up with n equals the square of that. And so that's where we get 2 million. So we're doing the same, very, very same thing. Let's, for the sun, with the proviso that we're also looking at how long it takes for each step. Each step is determined by the speed of light, how long it takes light to travel from between 2 points that are separated by the step length. So following that down, that's how we get the time component into this problem. And so basically the top line is we're going 1/10 of a millimeter per step. And then we're doing just simply the conversion. There are 1,000 millimeters per meter. So each step size is 10 to the minus 4 meters. And the distance we're traveling is 140,000 kilometers. So that's where we get that steps equals 140,000 meters divided by 10 to the minus 4 meters per step. And then we square that the way we did before. And then that gives us the number of steps according to the square root of n relationship. And then to get the travel time, we just find the travel time for one step, which is 1/10 of a millimeter. How long does it take light to travel that distance? It's going to be 1/10 of a millimeter, which is 10 to the minus 4 meters, divided by the speed of light in meters per second. And so that gets us that 3.3 by 10 to the minus 13 seconds per step. And so then we multiply seconds per step by the number of steps, and that gets us to the number of years after you've converted from seconds to years. And then we just repeat that for the exterior region, which has a different step size and a different thickness. So instead of 140,000 kilometers, we're now talking 550,000 kilometers. So is that sort of answering your question?
Yes, 98%. If you'll permit me to ask one last question. You commented on conversion in the first line. I'm still not quite following that part. I'm following every other part of your math now.
The calculation of the step size in meters.
Yes, your denominator where you have 1,000 millimeters divided by meter.
Yeah. Yeah, that's just a unit conversion.
Okay, thank you.
Yeah, I mean, you could rewrite this as 0.1 millimeters times 1 meter divided by 1,000 millimeters. And then you can cancel the units for millimeters directly. But then you get the factor of 1,000 in there, which gives you 10 to the minus 4 meters.
Okay, thank you.
Yep. All right. Other questions? I think I'm on a roll.
Okay, Matthew is asking if the Parker Solar Probe comes in on September 30th, how long will it take after the aphelion?
Yeah, the Parker Solar Probe is I think it's in a 90-day, 89-day orbit. So going from perihelion in December to aphelion is going to be about 45 days later. So it's about a month and a half, give or take. And so that'll be sometime in mid-January or early February, actually.
Thanks for the information.
The perihelion, I think, is Christmas Eve, right, Sten?
Yeah, nominally it's December 24th.
Was there another question? Gerald?
Yes, I think Tom had his hand up first, so
I'm sorry, I missed that, Tom. We can't let Gerald jump in front of you.
Oh, that's okay. But I'll go ahead and go. Somewhere along the way, you remarked one of the calculations for how long it takes photons to go from the center to the surface is anywhere from 100 to 1,000,000 years, 100,000 to 1,000,000 years.
Yeah.
And I'm wondering that's what I had read about.
Yeah.
And how are those figures derived? And compared to your calculations, what's the difference between those ways of looking at it and which makes more sense?
It all depends on the density model that you use for the interior of the sun. The simplest one is you take the volume of the sun, all right, and divide that into the mass of the sun to get kilograms per cubic meter. All right. To figure out how far apart particles are with that density, what you do is you take the average mass of the particle and divide that by the density, and then take the cube root of that. That gives you the average separation as though the particles were at the centers of their own respective cubes. And it's a good approximation. And so you see, as you increase the density, you are decreasing the distance, the average distance between the particles. That's why it's so crucial to get the density right wherever you happen to be located within the sun. If you just take the average density, which is what you get dividing the mass of the sun by its volume, you get numbers that are typically on the high side. It overestimates the actual density of the sun considerably. The volume where most of the density is in a very small part of the core. All right. And so if you leverage the rest of the density of the sun by smearing that density out over the interior, you wind up with artificially shorter distances between particles because you're not allowing for the fact that the outer layers of the sun are significantly lower density. So that's typically what happens when people do these back of the envelope calculations. You know, the first thing that you have to do is to come up with a plausible answer for what the density of the sun is. The alternative to that is you have to understand a little bit about how light is being scattered off of the charged particles within the sun. And if you think you know that number better, then you start with that number as your step size. So, you know, it's a matter of preference, and that's why you wind up with dramatically different answers for how long it takes light to get out from the sun. And in fact, it's such a goofy number for astronomers that astronomers, at least in the old textbooks, they tended to parrot whatever the previous textbook said that number was without actually calculating it themselves or bothering to. So you find earlier textbooks tended to propagate the number that, oh, it takes millions of years for light to get out from the center of the sun. And you see that in textbooks all the way into the 1980s. And then in the 1980s, you start getting textbook authors that were a little bit more thoughtful and actually tried to do this kind of a calculation. They didn't spend a whole lot of time with it because, as I said, it's a kind of a goofy number that has absolutely no astrophysical, sort of, benefit. But it's a kind of a fun number to calculate. And, it's like using the Drake equation to calculate the number of intelligent civilizations in the Milky Way. It's not that the final answer is an interesting answer, but it's all the gymnastics that you had to do to argue for the specific values on all the factors leading up to it. And that process actually has some educational merit to it. So, in effect, calculating the number of intelligent civilizations in the galaxy is a far more cogent activity for teaching astronomy than trying to reproduce this particular calculation, which has absolutely no benefit, at all. And so why am I promulgating this particular problem? I don't know. I'm kind of retro. I kind of find it a kind of a fun thing, and it's kind of simple math, and I get to talk about random walk problems, and that seems to have some mathematical benefit to.
Are you good, Tom? Do you need more? Okay. So Gerald, do you want to ask a question?
Oh, sure. Yeah, Sten, thanks for a fascinating talk, as I found all of yours are. Two parts to my question. I was thinking that if it takes 32,000 years for it to get to the edge of the sun, are there any considerations of the 8-minute time that it takes to get from the surface of the sun to us? I was thinking light, surely, or photons or whatever must be coming off at all different kinds of trajectories.
Oh,
Do
yeah.
they bend to each other or from other stars, hit light waves and so
Oh,
forth?
well, the really neat thing about photons is they do not interact with each other. So they pass right through each other.
All right.
And also the 8.5 minutes is the absolute minimum time of flight for a photon leaving the surface of the sun to get to the Earth. Now, of course, when it gets to the Earth, it's going to get scattered about a little bit in the atmosphere of the Earth, but not by very much, because the atmosphere is very low density. But yeah, I mean, most of the delay comes from the interior of the sun, and most of that delay comes from the region called the radiative zone.
Yeah. And then,
That's why we call it the radiative zone, by the way, because the dominant form of energy transport in the radiative zone is by photon streaming, which is this random walk problem.
second part of the question, then I thought, well, gee, there are lots of stars more massive than our sun. So certainly for astronomy, when we talk about how long it took light to travel, let's say to the James Webb or the Hubble, does this factor at all into the calculations of how long from massive stars it took light to actually get to the surface? Or is it
Yeah.
so small compared to what we care about
Yeah.
that makes
Well,
no difference?
those are completely independent calculations that have nothing to do physically with each other. I mean, that's why we can talk about the time delay inside the sun as being separate from everything else.
Yeah.
And that's the other thing that is worth saying is that the photon that is emitted by as gamma ray photons in the core of the sun from the fusion process, that's where they come from, is not the same photon that leaves the surface of the sun.
Mm.
So in point of fact, what you have to think about is that this isn't a random walk problem that's talking about how far a particular photon gets in its travel, but you should think of it as kind of like a wave of electromagnetic energy that's propagating from the interior of the sun out to the surface. And that wave originated at the core at a particular time. And at that point, it was formed by one population of photons. But then in the next instant, that energy was then carried over into another population that continued the journey. So,
Yeah.
There are a couple of different representations of this that are going on at the same time. But, for all intents and purposes, you can think of it as a random walk problem. It works out just fine.
Thank you. Very nice.
And there seems to be no, benefit or, discount to whether it takes a long time or whether it takes a short time for this radiant energy to get to the surface of the sun, because it's, the sun, its structure changes on timescales of millions, if not billions of years. And any time delay that's caused by the photons and traveling is just basically not relevant to the overall structure changes.
Thank you.
Now, of course, there are stars that are so massive that they produce a hellacious number of neutrinos, and those neutrinos carry off energy at the speed of light or close to it, and they're not affected by interactions with matter at all. And when neutrinos are produced in large numbers in the cores of stars, they escape from the center of the star instantly and get out within a few seconds or a few minutes. And this is actually a problem for the star because these neutrinos are carrying a huge amount of energy out from the core of the star, which essentially is like throwing ice cubes into an oven. You're essentially draining energy from the core, and of course that causes the core to start to collapse, and that's why you wind up with supernovae. It's from the enormous production of neutrinos and the leakage of these neutrinos out of the center.
Amazir, did you have a question?
No, ma'am. Thank
Okay.
you.
Anybody else have a question? Anything you want to revisit, Sten, based on the questions?
I've got a question.
Okay, go for it.
I find the fact that you approximated the problem so much more accurately by breaking the sun into two different areas fascinating. I'm curious how that would compare to the I don't know, perhaps using calculus to approximate it as the volume of gas decreasing as you exit the sun. I'm curious how those two approximations would compare, and I'm also curious what there was about the problem that suggested to you the two-part setup, as opposed to just, you know, average density.
Right. This is a standard way of approaching objects in the universe, especially ones that have spherical symmetry. We're familiar in astrophysics with breaking a star's interior up into multiple shells. Original calculations used 3 or 4, but modern calculations use literally thousands of shells. And these are all concentric shells, right? In each of these shells, the physical properties of the material there are slightly different. And as you correctly surmised, we can use calculus to sum up the contributions from each of the shells to get to our final answer. It's a very calculus-oriented approach to studying stellar interiors. And it also allows for the progressively more accurate estimates, for instance, of light travel times. You know, the one shell, one interior model gives you the worst answer of, you know, many millions of years. But even if you break it up into 2 shells, like I did here, you get an answer that's actually getting very close to what you get if you break the sun up into 100 interior shells and then do the individual calculations for each cell and then add those up, just like we did here on this view graph, PowerPoint slide.
And that calculation would get more and more accurate as we go to countably infinite shells, right?
Well, you don't have to go to an infinite number of shells because there are only a finite number of atoms inside the sun. And once you get to shells that have 1 atom per shell, then that's it. You've reached the physical limit of the system, right? So,
Yeah.
you know, typical calculations are performed, you know, based on the accuracy that you're trying to get to for your final answer, and also an understanding of how rapidly various physical parameters like temperature and density and pressure are changing. You want to have shells that are small enough that the changes look very smooth, you know, from shell to shell. If you take the shell and make it too thick, then you're going to get really big changes between the shells, and that gives you more inaccurate answers. So there's an optimization process of choosing the shell size against the particular physical parameter you're trying to model. It turns out density is very easy because it monotonically decreases from the center all the way out to the edge. And it's a power law kind of a relationship. So you can break that up into, you know, small numbers of shells or large numbers, and, you know, it doesn't really matter so much.
Okay, thank you. Although I did have to Google the word monotonic. How are you using it here?
Monotonic means basically one tone, one parameter, a linear change. To be monotonically decreasing means that it's decreasing at a constant rate, for instance, that sort of a thing.
Okay, thank you.
Good questions, Gabriel. Thank you. Anybody else stimulated to ask a question by all this? Great.
This would be a great science fair project, and you can play with Excel spreadsheets and come up with all kinds of interesting answers.
Okay, Rowena, do you want to ask your question?
Yeah. Mm-hmm.
Rowena was asking, can you unmute?
Yes, thank you. I was just wondering, talking about photons exiting the sun, could you please explain a little bit about what solar particle events are and why they're concerned for human space flight and satellites in orbit? Are they just a whole bunch of photons, or are
Right.
they something different? Thank you.
Yeah, solar particle events generally refer to the very high energy protons that are emitted by the corona of the sun when you have what are called coronal mass ejections that compress and accelerate the particles to very high energies. It turns out that the corona of the sun is laced with a magnetic field, and when you compress this field, the particles that are trapped in that field, they get pumped up in energy very quickly. So when you have a shock front like a coronal mass ejection emitted by the sun, it produces a region of acceleration where protons, for instance, can be accelerated to many millions of volts of energy. And it's those protons which are called the energetic particles, and those events are called energetic particle events. And these are the ones that do the most damage to people's health. So essentially, when you see a coronal mass ejection of certain levels of energy, you can usually expect there to be a solar particle event that comes at around the same time as you see the CME leave the surface of the sun, where the density is highest. For astronauts, basically they get very little warning from the time that the detectors detect these things to the time when the particles actually flood the space station. So you have to always be on guard for coronal mass ejections directed at the Earth. And then be aware that there might be one of these radiation events following right behind or actually in advance, because they travel at close to the speed of light, whereas the CME will arrive a couple of days later. So you know, it's complicated. With X-ray events, the X-rays can be very high energy as well. And in some situations, they almost act like physical particles instead of photons. And so when they slam into atoms in the upper atmosphere, they can strip the atoms, turn them into ions, and actually heat up the upper atmosphere as they deliver their kinetic energy into the atoms in the stratosphere and above. And so that becomes a problem over time for satellites that are in low Earth orbit, where they'll start to feel the effects of all of a sudden the atmosphere having a higher density, and so the drag is higher, and so their orbits will tend to decay over time very quickly.
Thank you.
Mm-hmm.
Another good question.
I think we need to start evaluating these on the basis of how good the answer was, and we need to have a show of hands. Was that a good answer, or did it completely miss the question you were just asked? I think that would be a very illuminating reverse evaluation.
Well, she thanked you, right, Rowena? So it must have been pretty good.
Yes, it was an excellent answer. Plus, I got some bonus information about X-rays. So thank you very much.
And I think the answer was mostly correct.
Well, no one is on. We have some experts on too, and they aren't correcting you. So that's a good sign too. Or maybe they're just polite.
All right, so next time I'm going to talk a little bit about these interesting objects, white dwarfs, neutron stars, and black holes. I'm probably going to spend a little bit more time talking about black holes. And quite frankly, I haven't the faintest idea what kind of math problems I'm going to cook up for these things, but I assure you they'll be interesting.
All right, well, I want to thank you all for coming, and I will email you with the link to the PowerPoint and the recording. So you'll hear from me, and please feel free to share it and encourage your friends to come.
Mm-hmm. All right, see you next time.
Thank you very much.
Bye-bye.
Thank you so much.
Farewell.
Bye.
It was excellent.
Thanks for your questions, Gabriel. Always makes it more interesting.
You're welcome.
Bye, man.
Bye-bye. Thanks for coming, Emma. Bring your friends.